Greetings and welcome, friends. 2.2, inductive and deductive reasoning. Nailed it. There we go. We're talking today about logic, good old logic. You know, you don't let us down. And here we are. We're going to start off with this core concept of deductive reasoning. You've probably heard of the verb deduce, right? Like Sherlock Holmes, someone mentioned, right? Right, it's kind of logically combining some ideas. Here we go. So when you use deductive reasoning, you start with two or more true statements and deduce or infer the truth of another statement. So we combine them. So here's two premises. No, premises sounds like I had to remove someone from the premises. The premises? I don't know. I'm not an English-atician. So let's see. It says premise number one. If a polygon is a triangle, then the sum of its angle measures is 180 degrees. Premise number two, polygon ABC is a triangle. Conclusion, therefore, the sum of the angle measures of polygon ABC is 180 degrees. Wow. So this pattern for deductive reasoning is called the law. Oh dear, I broke it. Here we go. No. Let's see. Whoa, breaking the fourth wall here, friends. That's okay. This is the law of syllogism, which basically, well, it says, yeah, if you have a true if-then statement, and then you have a case in which the hypothesis of that if-then statement is true, then the conclusion of the if-then statement applies to the case in which you are applying it to. All right, it kind of makes sense. The law it kind of just makes sense. So let's see what we can do. Let's do an example here, or a series of examples. And yeah, you might just need to follow along as best you can. It might be hard to write this much, so don't worry. Just follow and listen and enjoy. Let's see. The syllogisms below represent common types of flawed reasoning. Explain why each conclusion is not valid. Let's see. So here's statement number one. When it rains, the ground gets wet. Okay, so there's my kind of P implies Q statement. Then they said the ground is wet, therefore it must have rained. Thoughts? What is the flawed logic? The statement that I have relates to the conclusion, right? It wasn't meeting the hypothesis. So I can't necessarily use this inverse, the converse of this if-then conditional statement and assume that it's true because that hasn't been told to me. I do not know that Q implies P is true. All right, so that's wrong. Counterexample to this would be a sprinkler. Yeah. Counterexample would be an ice sculpture of Chuck Norris that melted. Didn't necessarily rain, right? Perfect counterexample. So their logic was they didn't have the hypothesis, okay? So not the hypothesis. And then they assumed that the converse was true. Let's see, B. If triangle ABC is equilateral, then it is isosceles. Okay, here we go. The statement we knew was that triangle ABC is not equilateral. It says, therefore, it must not be isosceles. This is an application of not P implies not Q, which we don't know is true based off of P implies Q. Right? If I flip those around like the contrapositive, I could make that conclusion with a couple logical jumps, a skip and a hop, if you will. But yeah, so that doesn't work. So they applied it wrong. Our statement, our case, did not apply to this if-then statement. Let's see, all squares are polygons. All right, sounds good. That's a P implies Q. Our statement is all trapezoids are quadrilaterals. I would say that's unrelated, right? Therefore, all squares are quadrilaterals. We're just like pulling a whole bunch of extra information that was not related to the original P implies Q. So, although all squares are quadrilaterals, it's not justified on the basis of this premise. Okay, this had nothing to do with the squares being quadrilaterals. We found like a correlation, but that was not causation. Let's see. So no triangles are quadrilaterals. That seems to make sense. So here's my kind of P implies Q. Is this one true in reverse? Are any quadrilaterals triangles? This one's actually, yeah, this one's true both ways. Quadrilaterals are not triangles, and no triangles are quadrilaterals. Let's see. Here's our fact. Some quadrilaterals are not squares. Okay? Therefore, some squares are not triangles. No, I don't think so. Because no squares are triangles, right? That doesn't work out. Also, yeah, it doesn't apply. This was not related to the P or Q in either of those instances. Okay, so that these were flawed. These were improper applications of the law of syllogism. Let's see. So that's deductive reasoning. When I combine statements into a new statement that is true, like they did here. This was the proper use that we saw. And they didn't give you more examples of that because the not cases were more interesting than the cases. Here's inductive reasoning. So deductive is combining true statements and deducing or inferring an additional true statement. Here, inductive reasoning, so if a conjecture is an unproven statement that is based on observations, okay? So these would be, you know, trends, patterns, okay, things like that. You use inductive reasoning when you find a pattern in a specific case and then write a conjecture for the general case, okay? So we don't necessarily know how that's going to work out, okay? We don't necessarily know those things. We are recognizing a pattern. We notice a trend, but there's not necessarily a guarantee that it has to continue, okay? But sometimes this type of reasoning still can be helpful in predictive measures. So in terms of data and statistics, when you drew a best fit line, extrapolation was when we kind of went beyond our original data set's domain or inputs. And interpolation was when we used our data's best fit line to predict locations within the data set. And like that kind of worked okay, but you might remember that extrapolation is less and less representative of the data the further out you get from your data set. So also, maybe, I don't know if you ask me someday, actually check out James Taunton. He's an Australian mathematician who lives in America. He's got a chapter of one of his books from the premise of not believing in patterns, and he actually can disprove any pattern, which is it's kind of interesting. Maybe I should link his YouTube channel in this. Let's see. So here we go. Example 1. You might not, I don't know, maybe you can draw a quick sketch of these things. Describe how to sketch the fourth figure in the pattern, then sketch the fourth figure. Let's see. So originally we have a circle divided into 2 sections. Figure 2, we divide it again. Figure 3, let's see. So we went from 2 to 4 to 6. So we weren't just doubling the number of sections, right? So I'm noticing a pattern. What's the number of sections I predict for the next one? 8 if this pattern continues, okay? And it appears to be shading. Which way does it shade? So top left, maybe? All right. So if I predict the next thing in the pattern, I should have actually used the circle tool. I'm expecting 8 sections. Oh man, this is so great. And maybe there's some disagreement on what I shade. You guys think this section right here? Yeah, I agree. That's what the book suggests as well. There we go. Shading in that. So so I've made my figure 4 based on the pattern, right? I was able to deduce that, and yeah, that's what we had. That's what we had. Let me give you one more. I'm gonna just do this one right here. So recognizing patterns. Patterns can be related to diagrams or number patterns, sequences and series. Let's see. So can someone verbally describe the pattern? We won't write down the pattern. Let's see. This was 1 ball. This was 3. This was 6. So I don't know. Here I was adding 2. Here I was adding 3. You guys think I'm going to add 4 next? Where should that 4 be added? It looks like these kind of all had roughly the same height originally, and that it's adding to the bottom here, right? Okay. So yeah, so my verbal description was add another row of balls to the bottom underneath the triangular arrangement in an equilateral shape. I don't know, something like that. So our 4th sketch would be, it would contain all that the 3rd one had, and then I'm expecting that it looks something like that. That's an awesome sketch. Look at that. When it snows, I'm going to go make an awesome pile of snowballs now. This is going to be great. Let's see. So making and testing a conjecture. Here's an example. Bing. So numbers such as 3, 4, and 5 are called consecutive integers. Make and test a conjecture about the sum of any 3 consecutive integers. Okay, so let's see if we can recognize a pattern. So actually, man, I so want to just open up a spreadsheet and then just like macro a formula and just apply it to a whole bunch of consecutive integers. It would work so well, guys. It's okay. Here we go. Let's do 1 plus 2 plus 3. What's that add up to? 6. Let's do 2 plus 3 plus 4. Let's see, 5, 9, yeah. Okay. 3 plus 4 plus 5, the case in question. Interesting. 4 plus 5 plus 6. Notice by my having a pattern in my kind of test arrangement, I'm able to do better predictions, like versus like if I was just like, I don't know, 101, 102, 103, like 1,022, 1,023, 1,024. Like you kind of want to like recognize a pattern by having consistent increments, so you can do better predictions. Let's see, this looks like 15. Guys, I'm thinking I'm starting to notice a pattern here. All right. We're saying 18. 7 plus 5 is 12 plus 6 is 18. Okay. So what's your conjecture? Now you might notice a relationship between these. What was this increasing by repeatedly? Right? That arrow was sad. There we go. These were repeated plus 3. Is there a way that I could relate either the first number or the last number to the outcome? Or the middle number? Interesting. Okay. So our conjecture statement would be that the sum of any 3 consecutive numbers is what? Three times the second number? Right, so that's a conjecture, and now we should test it. Okay, so we can test a few examples here and see if we can find a counterexample. Here, I'll work in blue here. So let's try 10 plus 11 plus 12. Our prediction is 33, right? 3 times 11. Right, actually I could write it this way. Is that equal, is the question, to 3 times 11? Does that seem to work out? 21, 33 equals 33, yeah. All right, how about this? 101 plus 102 plus 103. Is that equal, question mark, to 3 times 102? 3 times 102 is 306. Yeah. Now, we have, I don't know, maybe you have a degree of confidence in our conjecture, but I do want to point out we've tested it, but it is still unproven. All right? I would have to test this for infinitely many cases in order to, like, 100% know that it's true. Okay? So I don't yet know that it's proven. And even if it worked for 99% of cases but fails for one, it fails to be a true statement. And that's the idea. I've used this word already in the last couple days, a counterexample. So to show a conjecture is true, you must show that it is true for all cases. You can show that a conjecture is false, however, by finding just one counterexample. Wow. Wow. That's a lot of weight. Just one little bullet can just take this whole thing down. It's pretty crazy here. Right? So counterexamples, all it takes is a single example. Let's see, did I just have my mouse die? To disprove a conjecture. Let's see if we can find a counterexample for the following. All it takes is one. Let's see. A student makes the following conjecture about the sum of two numbers. Find a counterexample to disprove the student's conjecture. I love disproving students. That's just like gives me energy every day. That's why I wake up and get out of bed. No, I'm just kidding. But we can still learn from our mistakes, and we can refine our conjecture when it is disproven. Let's see. So the conjecture is the sum of two numbers is always more than the greater number. Okay. Thoughts? 2 plus 3, 5. That seems good. Jack, you got a counterexample?
5.
Yeah. 5 plus -1 is equal to 4. And notice 4 is not greater than 5. Man. Yeah, 4 is less than 5. I just was saying, yeah, 4 is not greater than. Yeah. So, yeah, we just ruined that student's day. They were hoping to get a college scholarship for that conjecture, and nope. That's too bad. That is too bad. Let's see. So deductive reasoning, we've talked about. Let's see. Here we go. I don't think we've talked specifically about. You know what? I might have made a mistake. We'll see. I might have to already edit this video. Maybe this student proved me wrong. So here's some laws of logic. I think I referred to the law of detachment earlier as the law of syllogism, which is a shame. But let's see. Here we go. So the law of detachment says if the hypothesis of a true conditional statement is true, then the conclusion is also true. Yeah, that's the law of detachment. The law of syllogism, I compare to the, I call this the transitive property of logic. That's my street name for it. okay, is how I describe this. Transitive property of equality, you might remember, was this. If A equals B and B equals C, then what was true? Then A equals C. All right, it's just like you linked these statements together, right? If A equals B and B equals C, then therefore the engine of the train is equal to the caboose of the train. We're just linking these together, and I have like a chain of equality, and I can relate any two of those things. That's similar to the law of syllogism. It says if hypothesis P, then conclusion Q, and if hypothesis Q, then conclusion R. Because these two things match, I can cut out the middleman, and I know that now if P, then R. Okay? Only because those match up just like so. Let's see. Let's do one example of the law of syllogism now that I've got it proper. Man, embarrassing, guys. Now I'm going to have to go and update this video in the future. So, if possible, use the law of syllogism to write a new conditional statement that follows from the pair of true statements. So let's see. Let's check this out. So if x squared is greater than 25, then x squared is greater than 20. Okay, that's true. Do negatives disprove that ever? No, because negative numbers squared will become positive, so that always works out. Let's see. If, second statement, x is greater than 5, then, hey, wait a minute, I saw this one before. X squared is greater than 25. So which way can I chain these up? I can write what? If, which one do I start with? Which hypothesis? It's going to be the second one concludes the first one's conclusion, right? Because it's if this, then that, if that, then this. So yeah, if x is greater than 5, then x squared is greater than 20. So they gave it to you in the opposite order, logically, than it was first presented, right? But if I wrote these in the other way, it would have been in the order that the law of syllogism was given to us. Let's see, how about this? If a polygon is regular, then all angles in the interior of the polygon are congruent. Okay, so let's see what I've got. Here's my hypothesis. Here's my conclusion. And wobbly lines. And let's see. Second statement, if a polygon is regular, wait a minute, that's the same hypothesis. And a different conclusion. Uh-oh. So I cannot combine these using the law of syllogism because these were both hypotheses. I can't link them that way. I don't have a way of linking. I need to link a conclusion to another statement's hypothesis so they don't link up. Unless one of these statements ended up having its converse also true, if it was biconditionally true, then I'd be able to make additional statements. But right now, I am just sadly unable. Well, friends, man, whew. These lessons, 24 minutes. Well, thanks for watching, internet friends. Above.